In this video lecture, we'll look at cell phones and driving. We'll first start by taking a closer look at the distraction caused by talking on a cell phone while driving. Then we'll take a look to see whether or not the same kind of distraction can happen while you're walking. And then we'll look at something slightly more disturbing, and that is the distraction of using a cell phone while performing open heart surgery. We'll start by looking at an American Automobile Association study that was done on driving behavior. In this study, they asked their respondents to self-report the distracting activities they had performed in the last month. The data is broken down by different age groups. We have new drivers between the age of 16 and 19, young adults between 20 and 24, adults between the age of 25-39, 40-50-year-olds, 60 to 70, and then people over the age of 70. The types of distracting activities that they were interested in were talking on a cell phone, typing or sending text messages or emails, accessing the internet, reading text messages or emails, and using social media. The first thing we note from this graph is that the most common distracted activity performed by drivers was talking on a cell phone. In fact, for the age group of 20 to 24-year-olds, almost 85% of that group had talked on a cell phone in the last month while driving. But this group also scored higher in most of the other categories as well. So for example, you'll see that they were most likely to have read or sent a text message. They were the most likely to have used social media, most likely to have accessed the internet. In fact, almost 30% had accessed social media on their cell phone while driving. If we look at the oldest participants, the 75 plus, you'll notice that they're not typing or reading texts or accessing the internet or using social media, but even this group has started to use cell phones while driving, and 40% of respondents over the age of 75 had actually reported using a cell phone while driving. Now, of course, it's worth pointing out that talking on a hands-free cell phone is legal in all provinces and all states. So it's not surprising to find people are doing this while driving. As part of the same study, the AAA also looked at attitudes that drivers had towards performing these distracting tasks while driving. So the first thing we'll note is that there was a higher perceived acceptability for driving while talking on a hands-free cell phone, and that was consistent across all age groups. There was also a high level of perceived acceptability for people talking on a handheld cell phone while driving, although you'll notice that the acceptability ratings does go down as the group gets older. Most participants all agreed that checking or updating social media or typing or reading texts and emails was not acceptable. In that 20 to 24 age group, you'll see only 10% saw that as acceptable. Keep in mind, however, that in the previous data, 30% of this group had actually done these distractions in the last month, despite the fact that only 10% of them thought that it was acceptable behavior. I'm going to focus on David Strayer's research. David Strayer is a cognitive psychologist at the University of Utah who has been doing distracted driving studies for a number of years. He uses mainly simulators in his studies. And driving simulators today are really incredible works of technology. Here's a picture of one. Instead of windows in the vehicle, we have flat screen TVs, but the actual cockpit of the simulator is an actual cockpit from an automobile. So driving these simulators is very realistic. But because it's a simulator, Strayer can also take all kinds of measurements. For example, they often have built-in eye monitors so they can determine where somebody is looking. They have measurements for all of the devices, so you can record how fast a car accelerates, how fast a car brakes, how fast someone reacts to a signal when they're braking, and so forth. So these simulators are wired up to take a number of different behavioral measures. In this particular picture, you can see that the driver is talking on a Bluetooth cell phone. Strayer always includes a hands-free and a hands-held version in his experiments, and it's worth pointing out that in every single one of his experiments, he has never found a difference between a hands-free and a hands-held cell phone. The distraction of these two devices are identical. Why that's interesting, of course, is that it is illegal to drive with a handheld cell phone, but it is legal to drive with a hands-free. As you'll see over the next few minutes as I describe this data, this has been done in error. A hands-free cell phone is absolutely as dangerous as a hands-held cell phone, and both should actually be illegal if we want to make the roads safer. One of the lines of research that Strayer has undertaken has been to look at whether or not participants who are performing this dual task of driving while talking on a cell phone have as good recognition memory for the objects that they view while driving as compared with drivers who are doing just a single task of driving their vehicle, for participants who are doing the single task of just driving. What he finds is that when you're driving while talking on a cell phone, your recognition memory for objects that you have looked at is 50%. And in fact, he's found that there's really no effect of fixation duration. It doesn't matter how long you look at an object. If you're talking on a cell phone, there's only about a 50% chance that you're going to remember seeing it. He's proposed what he calls the inattentional blindness hypothesis. And in this he states that what happens when you're talking on a cell phone is the conversation itself is the disrupting factor on your performance. It diverts attention away from the external environment where you should be attending while driving, and instead pulls your attention to the phone, where processing resources will not help your driving, and in fact losing those resources impairs your driving. And he calls this the inattentional blindness hypothesis. You might be thinking, well, what about strategically allocating attention? Maybe you don't need to see half the things that you look at while you're driving. There are important things that you need to see, like an elderly person about to cross the street. But there are other things that you would look at, say a billboard for a McDonald's restaurant, that you really don't need to remember. So the argument that's often presented is, sure, people miss half of what they're looking at, but not the important things. If it's something important that requires attention, then the person will have their attention taken away from the cell phone and reallocate it to the external environment. To test this, Strayer had drivers rate the importance of various items. So for example, an elderly person about to cross the street, or some children playing with a ball, or a vehicle backing out of a driveway were all rated as being very important things to notice while driving, while items such as McDonald's billboards or other signage or buildings were considered to be unimportant. Again, performance was significantly poorer when people were talking on a cell phone. Their recognition memory for objects was impaired when compared with people who were just performing the single task of driving. It didn't matter how long people looked at objects. People were basically, again, around 50% accurate at recognizing objects. But more importantly, there was absolutely no effect of how important that object was. People were just as likely to forget having seen some children playing with balls close to the street as they were forget a McDonald's billboard. Strayer also did an electrophysiology study looking at ERPs. We looked at event-related potentials back when we were considering the methods of cognitive science. These are the studies where you measure the electrical activity of the cortex. It's an excellent way to try to figure out what parts of the brain are operating at different times during a cognitive task. Of particular importance to Strayer's research was the P300 wave. The P in this case stands for positive. This is a positive shift that happens in brainwave activity at approximately 300 milliseconds following a stimulus. We know that the P300 is related to attentional allocation. If people are participating in an ERP study that involves allocating attention 300 milliseconds following a stimulus that people have allocated attention to, you'll find this particular waveform. And furthermore, it's been found that the larger the P300 is, the better memory people have for that stimulus. This makes sense because, of course, to remember something, you need to attend to it. Attention and memory are intimately related in that way. So a bigger P300 means you've allocated more processing resources to attending that item, and therefore it's more likely to have been entered into your permanent memory. If you have decrease in P300, that usually happens when participants are performing a complex task that's drawing resources away from their primary task. So whenever you have a dual task situation, you usually find a weaker P300 in response to a stimulus that under other conditions, a single task condition, would be much larger. So in this study, the participants were wearing the electroencephalogram electrodes while they were in the driving simulator, and they were performing what's called a car tailing paradigm. In this particular type of experiment, you follow behind a car, and the car that you're following randomly hits its brakes. And whenever that car ahead brakes, you're obviously supposed to hit your brakes to slow down to prevent from hitting it. This braking of the car ahead happens completely randomly. They started measuring the EEG at the point at which the car ahead started braking. This is the results that they found. So this is time across the bottom axis here, and this is the amplitude of the electroencephalogram, or the ERP, the averaged waveform. So this is a single task, and you can see that around 300 milliseconds following that lead car's braking, you see there's a big shift in 300. That's an indication that these drivers are allocating a sufficient amount of attention to their task and are likely braking quite quickly. But this is what happens when they are driving while talking on a cell phone. And again, it doesn't matter if that cell phone is being held in their hand or it's a hands-free cell phone. There is no difference between these two types of tasks. And we can see here that the P300 is about half the size. And what that's telling us is that there is not a sufficient amount of attentional resources available to react to the lead car braking. Now, I often get asked by students when I'm talking about cell phones and driving, well, what about passengers? If having a conversation on a phone is dangerous, wouldn't having a conversation with a passenger be dangerous too? And the simple answer is yes, it is. Passengers are a leading cause of distraction in motor vehicles and do cause accidents. But there's an important and significant difference between having a passenger in your car and talking on your cell phone. A passenger in your car is aware of this external environment that your attention has been drawn away from. They're paying attention, at least partially, to what's going on in the external world. So whereas you might not notice that little old lady about to step out on the street in front of you because you're in a conversation, you've got an extra set of eyes in that car. That passenger is also processing this information, and if they see the little old lady, they will adjust their conversation. They might warn you, or they might slow down as they're talking to make sure you... Right? So they can help out in the driving. So in this study, Strayer had some participants talking on their cell phone, either hands held or hands free, although it doesn't matter which condition since they come out the same. And then another condition where they had a passenger in the car. The task was really simple. Get in the simulator, drive 8 miles down the road, and exit when they see a truck stop. When there was a passenger in the car, sure enough, 12% of the drivers missed the exit. Perhaps they were too involved in their conversation to notice, but several of these drivers who missed that turnoff. But when they were talking on a phone, that number jumps to 50%. 50% of those drivers missed the exit. And the big difference here is simply that the passenger would help out. You'll often hear people try to draw comparisons between conversing on a cell phone and drinking and driving. Strayer has looked at this, again using the car tailing paradigm, where he had two groups of participants, one who drank until they were intoxicated at 0.08% blood alcohol level. This is in almost all jurisdictions the level at which it is illegal to drive, and it would be the equivalent of drinking 3 or 4 drinks in a 1 hour period. So it's a fairly high level of intoxication. A lot of jurisdictions have lowered this tolerance level to 0.05 or even lower. So they compared drivers at 0.08 alcohol intoxication with drivers who were talking on phones. Now, I mentioned before that these driving simulators can measure a lot of different types of responses. This is a kind of a breakdown of what was measured in this study. So along the bottom axis here we have time. At some point the car you're following hits the brake lights. So what Strayer is able to do is he can measure the point at which the driver starts hitting the brakes and how hard the driver hits the brakes. There is a measurement of what the pace car's speed is. There's a measure of what the driver's speed is. There's a measure of how far behind the pace car the driver is. And all of these variables can be analyzed to look at the safety of the drivers who are performing this cartailing task. Now, there's a lot of data here. I'm just going to kind of cherry pick some of the more interesting data, but we can compare three conditions: 0.08 alcohol, a baseline condition who are people who are sober and not talking on a cell phone, and people who are talking on a cell phone. I want to go first to the brake reaction time. And you'll notice that if we compare the brake reaction time, there's actually very little difference between the alcohol impaired and the baseline condition. The cell phone condition, though, you'll notice is much slower, almost 70 milliseconds slower in braking. If we go to the maximum braking force, we can see a difference here with the drinking drivers. The cell phone users and the baseline users use approximately the same amount of braking force, but you'll notice that the drinking drivers use quite a bit more braking force. We'll see below why this is probably happening. In terms of speed, both the drinking drivers and the cell phone drivers have reduced their speed a little bit, probably because they are aware that they are driving while impaired. Now, if we look at the mean following distance, this is how far behind the pace car you are. You'll notice that the drinking drivers follow at a closer distance, a meter or even 2 meters closer than the cell phone drivers. This is likely why they hit the brakes with more force. They're following more closely, and so when the car ahead of them brakes, they hit the brakes with more force to try to slow themselves down faster. This is the time to collision. This is how long, if you do what you continue to do without changing your behavior, how long before you collide with the car ahead of you. This is a more important measure. This is how often you get within 4 seconds. Now, in this condition, this time to collision less than 4 seconds means that if you do not take immediate action, you will collide with the car ahead of you within 4 seconds. You'll notice that the drinking drivers, again, tend to get themselves into this situation more often than either the baseline or the cell phone drivers. And again, this is probably why they're hitting the brake with more force than the other two conditions. If we look at the recovery time, this is how long it takes you to get out of that dangerous situation. So the car ahead of you is braked. You get too close to it, you brake, slow down, and pull back. This is a measure of how long it takes you to get out of trouble. You'll notice that the cell phone drivers here are slow. They're slow to get out of this danger zone after the car ahead of them brakes. There's two things going on here. The cell phone drivers are reacting very slowly. They're driving perhaps a little cautiously, but their reaction is slow and they're getting themselves into dangerous situations. The drinking drivers are different. The drinking drivers are following too closely and they're hitting their brakes too hard. But there's another important difference between the two groups, the group that was drinking and driving and the group that were using cell phones. And that's on the top line here. The cell phone users, 3 of the 18 participants, rear-ended the pace car. The drinking drivers, despite following too close, hitting the brakes too hard, and so forth, have never once had an accident. And yet 3 out of the 18 cell phone drivers had to terminate the study because they rear-ended the pace car. Fortunately, it was a simulation and nobody was hurt, but it shows you that, in fact, conversing on a cell phone and driving is at least as dangerous than drinking and driving, and perhaps even more dangerous than drinking and driving. And remember, there's no difference between a hands-held cell phone and a hands-free cell phone. This problem exists in both cases because it's not holding the phone that's causing the problem. It's the conversation with somebody who is not in the car and is not aware of your external environment. Well, if it distracts driving, what about walking? Hyman did a study looking at people who were walking while talking on a cell phone. They looked at people crossing Red Square on the Western Washington University campus. This is a square where there's really just one route to get across, and it's along a path where a lot of students are crossing in between classes, cutting across this quad to kind of take a shortcut to their next class. They took a number of measures. They looked at how long it took participants to cross the square, whether or not they changed direction. They looked at weaving back and forth, whether or not they acknowledged other students by saying hi or waving, whether they stopped, and how many near collisions they had where they almost walked into somebody. There were 4 different groups that they looked at: people who were talking on their cell phone, people who were walking by themselves, people who were walking by themselves but listening to a music player, and people who were walking in pairs. In terms of crossing time, you'll see that talking on a cell phone or walking in a pair both slowed down the amount of time it took people to cross the square. There was a big effect of changing direction. You'll see that 30% of the cell phone users were changing direction as they walked across the square. Compare this with less than 5% of people who were walking by themselves. There was a bit of that happening with the pairs as well, but nothing as pronounced as the cell phone users. Same thing happened with weaving. The cell phone users tended to be weaving back and forth at a higher rate. Single walkers do that as well, but again, it's the cell phone users who are doing most of that weaving. You'll notice that while walking and talking on the cell phone, only 2% of this group acknowledged other people or said hi or waved to other students. Compare that to over 11% of students who were walking by themselves, 13% of students who were using a music player. Even people walking in pairs were more likely to acknowledge other people while walking. We find that cell phone users, 4% of them stopped. That's twice as many as single users. This was also happening with people using their music player and their pair. The near collision data, I think, again, tells an interesting story. 4% of the cell phone users almost ran into somebody. That didn't happen at all with single people or people walking in pairs, and it was pretty rare to happen with people listening to their music player. So you can see there's an indication here. It looks like people are somewhat impaired while they're walking and talking on their cell phone. In the second part of the study, it turns out that there was a little more than just walking across the square. They had positioned in the square this clown here you see, riding on a unicycle, bright red sneakers and a red nose and purple uniform and polka dotted shirt. Not the kind of thing you typically see on a university campus. So as they walked across this quad area, they would have walked right by this clown. When they got to the other side, they were asked 2 questions. First, they were asked, did you see anything unusual? And then, depending on how they answered that, they were asked specifically, did you see the clown? And these were the responses looking at the various walking conditions. The general question, did you see anything unusual? Only 8% of the cell phone users reported seeing anything unusual. Compare that to 32%, roughly 1/3 of the single walkers and the people walking with music players. Notice that the best performance were actually people walking in pairs. You'll recall that I had mentioned that the difference between having a passenger in your car and talking on a cell phone is that the passenger provides an extra set of eyes to watch in the environment. So here you can see the effect of having the extra set of eyes where pairs of people were more likely to notice the clown. Now when asked specifically, did you see the clown? You'll notice that the cell phone users, there's more that answer yes to that, but still only 25%, only 1 in 4 people talking on the cell phone actually noticed the clown. This is half as many as in the single condition. Again, if you go to the pair, you see the pairs are more likely to see the clown simply because you've got that extra set of eyes looking for it. But the comparison between the person walking by themselves and the cell phone user is quite striking, with only half as many cell phone users noticing the clown. There are other inappropriate venues where multitasking may be happening, and one of those is during open heart surgery. Perfusionists are the surgeons who keep you alive while a surgeon is operating on you. So they are in charge of your oxygen supply and monitoring your vital signs to make sure that you're still alive. They play a very important role in open heart surgery. Smith and colleagues did a survey, and this was a number of years ago, so it was before the big explosion of social media. Nevertheless, there were cell phones, and many surgeons had cell phones at the time. In the survey, they had people report how often they did the following things: talking on their cell phone, texting, emailing, browsing, or accessing social networks. And if we look at the percentage of perfusionists who reported these types of behavior during cardiopulmonary bypass, we can see that more than half of them reported using their cell phone during surgery. Approximately half of them reported texting. 21% had reported email, 15% reported browsing the internet. We only have 3.1% reporting using social network, but of course this was before Facebook, and likely if we redid this data we would see a much higher report of social networking as well during cardiopulmonary bypass surgery. This is a bit disturbing because the perfusionists are the doctors who are there to keep you alive. Now, interestingly enough, if you ask perfusionists, is this kind of behavior safe? 78% said it was a significant risk to patients for the perfusionist to be distracted during the surgery by accessing their cell phone. We saw this before in the earlier data where people report at a higher rate that there are dangers associated with, say, talking on a cell phone or texting while driving, yet you see higher numbers of people doing it. Often our behavior and our beliefs about whether or not our behavior is safe contradict each other. And this is certainly a case here where I think the perfusionists have it right. This is a significant risk to patients, but unfortunately, they do the behavior anyway. Okay, next you should read section 4.5 of your textbook. That starts on page 105.